This is Clarice. I work at IBM. I'm an IT architect. I help clients build up their AI infrastructures and use cases. We do a lot of workshops, demos, and proof of concepts as part of the Worldwide Client Experience Center. This afternoon, we're going to cover some tools and tips that will help you with the hackathon that we talked about this morning, but for completeness, let me just recap what it's about. It's a hackathon that's sponsored by your organizations here, OpenPOWER Foundation and IBM, and it'll be kicking off today and ending May 3rd. The goal of the hackathon is to see what can be done when you focus on accelerating your AI. So what we're going to do is have you pick a model that you're familiar with or that you start from scratch with, machine learning or deep learning, that runs on a CPU or maybe a single GPU, and you're going to have 2 weeks to work through some tools and techniques to accelerate that training and see if you can train and get a big improvement in 2 weeks using some of the Power AI information that we're going to give you on our power systems. There's the prizes associated with this, courtesy of the OpenPOWER Foundation, and criteria and all that information is going to be available in a box folder with details from those criteria and everything else that we talked about this morning. So just as a reminder, you're going to pick a model and you're going to look to see how to accelerate it using the facilities that you have here at Virginia Tech. When we get through my presentation, Robert will show you how to log into the resources, and then I'll show you on my system some of the places you want to go to find the various readmes and so on. So what I'm going to do for the rest of the session here, we're going to focus on tools that will let you go from a single GPU to multiple GPUs, how to accelerate your codes using libraries that are basically done the acceleration for you. And you're welcome to use any other innovative approach that you come up with as part of this. You'll have a 10-minute, although I hear we have even more teams than I thought we would, so it might be somewhere between 5 and 10 minutes to show your results, maybe through a Jupyter notebook or whatever else you want to use to convey what you did for this hackathon. Okay, so let's get started on why we're here and what kind of tools IBM has been working on power systems to help you build models at a faster pace that train quickly and accurately. So why are we here? We're going to cover what's driving the AI interest in the market. We'll look at some use cases, and then we'll go through some of the tools and techniques that we have available that are installed on your cluster. You have a Power 8 system. I think it's 12 nodes. Each node has 4 GPUs, 4 NVIDIA P100 GPUs. And as we mentioned, the winners, and maybe some of you that are interested in pursuing this after the hackathon, we can look at what kind of performance you might get at even larger scales and on the Power 9 AC922, which is our current node offering. So use cases are everywhere. And basically what I mean by a use case is anytime you have a system or a human that sees, that hears, or that can do something, if you can mimic that expertise, whether it's vision, hearing, or maybe a chatbot of specific rules that you apply to do something, you're talking about AI. So we've done use cases, for example, with the TSA to do object recognition in their screening process to enhance what the humans see on the screen and accelerate, hopefully, the process. They're also looking at 3D screening in the future, which will be even more complex. We've worked with railroad companies to listen to the tracks and the engines and look for defects through some deep learning models that translate sound into a visual representation of that sound and then does deep learning against that. Pretty interesting. And then we do a lot of things with our Watson products to build chatbots and sentiment analysis that you can incorporate into larger models. So what's driving this? We've had an explosion of data. I think all of you probably have seen a minute in internet time and how many messages that represents across all these apps. You've seen Twitter, Facebook, Google, just generating and collecting a lot of data. So there's a lot more information than we've ever had before, and it keeps growing. We've also had breakthroughs in algorithms in the last 10 years that make the theoretical practical. And with that improved algorithm, having access to GPUs, FPGAs, and accelerators, you can now train models in a time that makes it more efficient and effective. We'll talk about some use cases in a little bit. I just wanted to point out that universities and Virginia Tech, are the center of this. It's universities, research labs, and industry that are pushing this, but what we need from you is to get familiar with the machine learning and deep learning techniques, and use what you're learning in school to advance the state of the art. And I've got a couple examples. This is an MIT example. I think if I hit, they created a data set with 1 million videos that each little snippet of video represents an action. So there's some ideas here relative to building models maybe that uses this data set that can advance the state of the art in video analysis, for example. Another example is drug discovery. This has money attached to it, so you have a good chance of finding jobs and getting funding for your research. If you can work in this area where you can show that limiting the number of false starts will get you to an approved drug much faster, much quicker. And you've got your own researchers here. I don't know if anybody knows Dr. Wu Feng. He's a great guy. Yeah. He's got all sorts of hands in all of this, merging computing with science and industry to get results. So the issue with AI today is scale, time. You can't scale and you don't have enough time. And when you just use CPUs, you're just not getting fast enough. This is a marketing guy did this for me. It's pretty fancy, right? So you need GPUs. They're great for matrix math. I think we all know that. And the combination of the two and feeding a pipe between the CPU and the GPU that gets the data to the GPU so that you can have your GPUs be as efficient as possible is really the key to success. Same with memory. You want to make sure that you are not inhibited by the memory on the GPU for your training, and that you can leverage all the information that you can. So IBM and NVIDIA have worked on this NVLink 2 technology, which is just bigger pipes between CPU and GPU to GPU communication. And all of that is built into the tools I'm going to show you. You don't have to think about, whether you're efficiently using NVLink. It's there, and that's the idea, is pulling it out together and getting more accuracy from your models in a faster time frame. So today, a lot of folks use Scikit-learn as their go-to for machine learning. There's some challenges, I mean, there's some positives. Lots of models out there. GitHub is full of examples that you could maybe use that as one of your starting points. A lot of good documentation on how to use the calls, the APIs that they provide. Very standardized, so if you're used to working on x86, you should have no problem bringing it in and work on the power systems. And some of the things that are inhibitors are the lack of deep learning support today, in particular parallel deep learning, distributed deep learning, and not that great for very large data sets. So we are addressing these with our own framework. It's using open source frameworks that you're familiar with, like TensorFlow, PyTorch, but combining them together so that you have a good environment where you're not spending all your time setting up your environment. You can go straight into the machine learning and deep learning. We recently rebranded Power AI because our Watson team really likes what we're doing. And so now it's called Watson Machine Learning Accelerator. And it'll be even more tightly integrated with Watson APIs over time. So that's for the first issue. For the second issue, we have researchers that have developed a library called SnapML that is really outstanding relative to performance, which is why I'm mentioning it here, because it could be a great advantage to your models if you just start using SnapML instead of scikit-learn, for example. So our strategy is to look at this holistically. It's not just about hardware. It's not just about the right software. It's having that combination of the large pipes for communication, the right CPU and GPU technology, but also the software stacks to make it easy for data scientists to build models. And eventually, once we get to steady state and want to get into production, to make it easy to manage teams of data scientists, schedule resources, and go into production mode with a lot more things to juggle at the same time. But you guys don't have to worry about that because we're going to focus our time here on this Watson Machine Learning Community Edition. And that's what's installed in, on the Virginia Tech system. It's known as Power AI 1.6.0, latest and greatest version that the team is installing for you, so you'll have access to everything that we've put in most recently. But just so that you're aware, it's part of a bigger architecture where you have your open source models, and this is for the data scientists that understand Jupyter Notebooks and that understand the models that they're creating, et cetera, et cetera. You've got a layer above it, which is for this auto machine learning and auto deep learning. So it's kind of point and click type models. So you're not digging down into you know, how many layers your model has or which model to use. They pull in best of breed models to do vision, object classification, segmentation, and detection. And H2O Driverless AI is a partner of ours. They have a product called Driverless AI, which is terrible for statisticians because you import your data sets, your spreadsheets, and it'll do everything for you. It'll create all the visualization of your data. It'll recommend which model to pick for which accuracy you're looking for. It'll tell you how explainable your model is. It's really, really nice for structured data, especially like financial data and financial services. So very popular tool, but does not really require computer scientists on each of those. It just requires the ability to understand and interpret what you're doing, so subject matter expertise. The other thing we have to get to production and to help large-scale models is Watson Machine Learning Accelerator. This is free, this is for fee, and it allows you to distribute your deep learning across a much larger number of nodes. It has auto hyperparameter tuning engines where it'll use the resources that you have to determine what the optimal hyperparameters are for your model. It has a deep learning module that takes you from data prep to training to inference and gives you a lot of hints and tips along the way, but more geared towards the data scientists and also the system administrators that have to manage all of this. They get IBM Spectrum Conductor with Spark, which is our scheduling engine, and offers the best way to distribute your resources in a larger environment. So like I said, we're going to focus on the Community Edition. This has a lot of the frameworks and all the popular ones today. TensorFlow, that also has the Keras, TensorFlow plus Keras, which is very nice and easy to use. TensorBoard, which will offer you a lot of good visuals on what your model is doing. Caffe 2 are supported. PyTorch is the newest addition to what's in there. And then we also have all the tools, open source tools and others that manage these frameworks, especially in the distributed deep learning environment. And we have libraries like SnapML and NVIDIA Rapids supported as well. So the advantage here of Community Edition is because your support staff has installed Power AI 1.6.0, you're getting all this working together, and you don't have to spend a lot of time installing, trying to find prereqs, and so on. It's all built with Anaconda under the covers. So you build this. If you find that you're missing a package that you really care about and it's supported, you can install it with Anaconda. And it's just Linux, so if you have other tools and other things that you want to do, you should not worry that it's Power Systems as opposed to something else. So it's a really nice environment that lets you get straight to work, basically. So as I mentioned, so we curate those open source packages for you. We test them. We pre-compile the frameworks. And basically that lets you have access to the large model support feature, which is something new and different that we'll go over. We'll then go over the distributed deep learning capabilities that come with Community Edition, and the software libraries like SnapML and NVIDIA Rapids, and how you would use those in this environment. I'll stop here. Any questions so far? Okay.
Can you kind of describe a sort of an example problem people have worked before for the same kind of hackathon, so that it can give us a kind of a flavor or gist what kind of
like
problems?
This?
Yeah.
Okay, great. We're going to cover some AI examples, and these are use cases across a lot of industries. I could spend a whole day picking each industry and talking about examples of where AI makes a difference. And some use cases are across all industries. But what I did is I just picked a few across a couple just to give you a sense of this. So as you're working for your project, on your projects, if you can tie your model to either something that's useful across all industries or solves a problem for a specific industry, that's good background to build your case. So think about it in those terms. So go through a couple examples. Everyone knows about the automotive one, right? Every generation of car now has some new features that keep you awake, keep you in the right lane, tell you if a pedestrian is coming across, et cetera, and eventually will be thinking of autonomous driving as the norm as opposed to the exception. Although it's even not that much of an exception anymore. Has anybody been to Phoenix? You can get, I can't remember what I think it's the Google version, Waymo. You can drive, you can get like an Uber-like ride from an automated, purely automated car already. So they're out on the roads. You don't know it yet, but they're there. This is the example I was talking about earlier, using sound to recognize any engine problems. This is the matching problem set here, looking for defects from a visual perspective on quality inspection for trains, and that applies across many, many different industries. We have a lab in Singapore that looks at DIMMs and has a robotic arm that picks up the DIMM, looks for the defect, and then sorts it based on what it finds from a visual perspective. So it's being used in industry as well. I'm low battery, so I'm going to stop and plug myself in. Okay, it was happy. Let's keep going. Any questions? All right. Security and public safety, you saw the TSA example. There's a lot of work here on not only just visual recognition, but also sentiment. You know, does this person look happy, angry? It's interesting because it starts to bring in a lot of the ethics in AI, with and looking for bias in AI and so on, which our research arm with IBM OpenScale is looking into as well, and supporting the work we do. But that's an example. There's another example of people counting in crowds and tracking motions in crowds. So this is a combination of vision models and other tools to build applications around the models that you train. Let's go to banking examples. This is an ATM demand forecast example. It's I show it because when you talk about use cases, it's very easy to end up talking just about vision models because they're fun, right? And you can see what you're doing. But this is a case where they used neural networks to determine when they were running out of cash, to predict when they would run out of cash at an ATM. Yeah. Consumer, they're everywhere in terms of examples. Some you may not even be aware of. This is Louis Vuitton looking at sentiment in pictures to determine whether sellers are selling fake Louis Vuitton bags, name brand bags, and that actually, I guess, saves the money because the less counterfeit product they have out there, the more they can sell the real stuff. Another fun example is Oil of Olay is a brand for facial products, creams and things like that from Procter & Gamble. And they have something called a skin advisor on the web, where you take a picture of you take a selfie, send it to them, and they come back with a report on your skin age and problem areas and recommended products. Well, believe it or not, something that simple is actually generating revenue for them because people are buying the products that are being recommended, and they're staying on those websites much longer than they would without this kind of personalized interaction. So personalization is a very important feature in machine learning and deep learning. And how they built that model, from what I read in the press, is they asked all 50,000 employees to volunteer their faces. So they started with the database, and now I'm assuming they have even more images because people keep taking selfies and sending it to them. So really interesting application, which, you know, you have to kind of connect the dots to get to why would you do that, and how do you get there to do that. So a little bit more boring, but pretty interesting if we've got any math types in this room. This is optimizing the warehouse path. So you have a number of things that you want to pick up from a warehouse, either by hand or robots or whatever. And you build a model that says, start here, follow this blue path, then loop around and get that product, then loop around and get this product, and so on. Come around, get this. And it basically gives you an optimal path for how to pick up the objects that you want in your warehouse or in your store or whatever. So this is applicable to other cases as well. But kind of interesting and innovative in the sense that there's really no visual representation of this unless you do something outside of the model and kind of show how it works out. All right, healthcare, medicine, biology, that's a big one. It's in the news a lot. This is an example of helping radiologists who are few and far between and very busy and eye fatigue maybe at the end of the day because they're so busy, to help them look for the right things. This is a blood-based disease that was based on visual recognitions. So there's a lot of examples in this field as well. A lot of it is visual models. Energy and utilities, very common use case is vegetation management of their power lines. Also looking for defects in their insulators and lines and substations. And this is an example of wind power prediction for machine learning. So this is an example that used the SnapML library accelerator that I mentioned earlier. So I'm going to conclude this section on use cases. I hope that addressed some of the questions you had. I want to conclude with this picture. It reminds me to talk about what IBM Research is doing. They're doing some pretty amazing things with ocean health, for example. They have little cameras that are going out into the ocean and looking at plankton health, and based on that, building models for ocean health. They have that a food chain project going on where you have the provenance of your food at every step of the way, and you're using AI techniques and blockchain to validate the food situation so that you don't end up with E. coli in your romaine lettuce or whatever it was. So they're doing large-scale, life-changing kind of projects. And it's not just IBM, it's the researchers in the national labs that are looking at all of this that will eventually impact our daily lives. So I'll stop here again and see if anybody has any questions or wants to ask about other industries or the difference in the different models that we saw. Yeah. Yes, it's available on. It's available in the Power AI distribution that you have for this project. Okay, so let's talk a little bit more about some of the performance examples on how to get AI at scale. One of the most popular, this doesn't render too well, but if you've heard of ImageNet, it's a 1.2 million library of images. I would use pre-trained versions because it'll take weeks to train from scratch on this. And they came up with, in 2012, a new model called AlexNet, based on convolution neural network, that was significantly better than any vision recognition tools prior to that, which were basically getting things wrong 28–30% of the time. So this was a significant jump, and in the last few years, it just keeps getting better. Does anybody know what human error is about? Where would it fit in this chart? Here, between 7 and 4% is average human error rate in recognizing, you know, and you've seen examples of, you know, you think it's a cat, but it turns out it's really a dog because, you know, you missed the ear that was hidden or something. So that's why it's interesting to industry in particular, because now you're doing better than your human inspectors, for example. So this is going to help them do a better job because it's going to catch some things that maybe they wouldn't catch, and also be more consistent between, for example, different quality inspectors. So this workload, so ImageNet, so there's two things. There's data set, so that's the ImageNet, is the data set, and the model is all those examples that I showed in the previous chart. In this case, ResNet 50 or ResNet 101. The number after it is the number of layers in the convolution neural network. And it shows that from one system to 64 systems, using all the GPUs, you can go from a 16-day training cycle to 7 hours, which is really significant. And from GPU to GPU, you're basically getting linear scaling or near linear scaling, which means that if you invest in a larger cluster, you're getting benefit from all the resources of that cluster, and you're taking advantage of the speed up that you naturally get basically from adding more resources. The same type of workload was run at Oak Ridge, and this is on a slightly larger number of GPUs. It's not as big as some of the HPC examples where they've run on 2,000 nodes that, you know, that show scaling. But this is the same idea. In this case, they used Keras and TensorFlow, and they used Horovod as a distributed engine. We have in Power AI the equivalent. It's called distributed deep learning, DDL, and I'll show you how to use that. And just of interest for you is the platform you guys are running on is the blue columns. If you have an opportunity to run on the Power 9, which is what is on the Summit systems and our latest generation servers, you'll get a speed up. I've seen a lot of cases with about 2x, 1.5 to 2.5. So the point here that I'm making is you're going to get good results naturally by adding more resources. Where the challenge will start to come is how do you effectively get the most out of the resources. And you may need to go back and say, you know what, our data set is just so small that it already runs and the GPU is only, you know, 10% busy, so adding another GPU is just not gonna help. So that's the kind of work that you're gonna wanna consider as you build these more performing models by leveraging basically more resources. The other thing you can do is look at large model support and come up with some scenarios where you're running with less information and smaller images, for example, to a case where your images are much bigger and can't be managed well with a small CPU to GPU pipe. And here you would look at something that helps you load up the GPUs better with this feature called large model support. So that's an exclusive, I guess, for the Power AI 160. But there's no reason for you to need to use it if your use case isn't bringing in, for example, larger images in your data set. But it's something to consider if you come across a use case, or if you're working on a use case that could take advantage of this. And this is run actually on a Power 9. It just shows that you're getting, you could run basically 4 times the number of training models in the time it takes to do one, because you're not breaking up your image into manageable pieces. You can go straight to the large image input with large model support.
When you say large model, is that the input dimension is larger?
Yes.
It's not the fixing number of.
No, it truly is the Mona Lisa in color at a bigger size versus the granular input.
So what's the number from the scale? How much?
So if you look at it at the example here, we used instead of 224 by 224 on a regular image net, the images were enhanced to be 2240 by 2240, 100 times bigger in pixel counts. And here's a real live example. This is a 3D UNet segmentation model, again visual, but it looks for brain tumors in 3D. And you don't want to cheat on the resolution of your images when you're looking for a brain tumor, right? The more precise you can be, the better the chances are that you identify exactly where the tumor is, as opposed to neighboring areas. So this is just the example of running a lot faster, time per epoch, which is training. You run multiple epochs to refine your model. And this is NVIDIA's NVProf tool, which is also very nice visual to show whether you're doing something with your model. You can see a lot of blank spaces where the GPU is just not utilized. And on the AC922, the memory copies are basically happening in parallel to feeding the GPU. So now your GPU is a lot busier, which is good, because that means it's doing more computation in a smaller amount of time. And the width of this represents the time it takes without overlapping memory copies relative to the time where you can overlap the memory copies, because you have a faster pipe between the CPU and the GPU for these large images. Okay, the next example I have is SnapML. It sounds like I have all the gear to play this little video, and I think we have time. So I'll let the research experts who built this tell you about it. They'll do a much better job than I do. So, but that would imply starting the volume. Hold on. Sometimes it works better. No sound. And it's not me. Maybe if I unplug this, you think? No.
It's from optimized hardware
Yeah.
architectures, such as.
All right, so we'll unplug the sound from the system just for a minute.
Minimize.
Oh, we had it, but now we don't. Let's try again.
Snap Machine Learning is a new library for fast training of generalized linear models. It combines innovations from algorithms and software and benefits from optimized hardware architectures such as IBM Power and NVIDIA GPUs. It builds on recent advances from parallel and distributed learning to remove the training time as a bottleneck for a range of applications. Workloads where training time can be critical are, for example, real-time learning, where frequent retraining of models is desired, ensemble learning, where a large number of models need to be trained and combined, and also large data applications, where even the training of simple models can be very time-consuming.
The three main new innovations in Snap Machine Learning are new algorithms designed to run on GPUs, efficient use of sparse data structures, and the ability to scale out to many nodes while keeping communication at a minimum. The library has a flexible API, which can be used in a standalone mode via Python interface, or it can be used in a distributed mode via an Apache Spark or MPI interface. Using Snap Machine Learning on IBM Power and NVIDIA GPUs, we were able to train a logistic regression model on the terabyte ClickLogs dataset in under 2 minutes.
The terabyte ClickLogs is a large online advertising dataset released by the Criteo Labs in order to advance research in distributed machine learning. The dataset consists of a portion of Criteo's traffic over a period of 24 days, and every day over 160 million training examples were collected. So the whole dataset consists of over 4 billion labeled examples, where a label indicates whether a user clicked on an advert or not. So the machine learning task is to predict whether a user clicks or does not click on a particular ad.
So SnapML is particularly well suited to IBM Power and NVIDIA GPUs. So when the data set is really huge and it doesn't fit in the aggregate GPU memory in your cluster, we have to use some techniques for swapping the data in and out of the GPU memory. So there are various ways we can do this to try to minimize the amount of data that has to be swapped. But in the end, for some applications, this time to copy the data from the CPU to the GPU can still become a bottleneck, in particular when one's using the PCIe interface. So the NVLink interface is a high bandwidth interface, so we can leverage that additional bandwidth to effectively hide this copy time behind the computation time on the GPU. What this means is that we can use the GPUs more effectively, and that results in a faster training time in the end.
I guess that clicking was part of the soundtrack. I have a couple more charts on SnapML, but anything on the video? They talked specifically about the NVLink and hiding the communication paths between CPU and GPU as a result and getting better performance. The data set they use is a big data set for web analysis, web access analysis. So to recap, framework for machine learning models. So not used in deep learning, convolution neural networks. For example, it's labeled, you need labeled data to do supervised machine learning algorithms. Down at the bottom left here is just a quick refresher. When we talk about deep learning, we're specifically talking about neural network models. When we talk about machine learning, we talk about supervised and unsupervised techniques that use structured or unstructured data, labeled or unlabeled. And artificial intelligence is the bigger envelope of that, which would include things like robotics tied to those models, or basically anything that does something for you that would require some of these models to be built up, or chatbots fit in there, sentiment analysis, things like that. So why fast? That's why we're here for this hackathon, is to go fast, right? So it's important to have models that train faster, because once you train a model, very often things change, patterns change, trends change. You get new information, especially like, for example, the automotive area. As soon as they find a mistake, they build that back in and retrain the models. So you need to be able to have quick turnaround on training your models so that you can always stay up to date, especially in critical functions. You want to be able to pick the best parameters for your model to improve accuracy. And the faster you can train, the better off you are. So a day in the life of a data scientist could be, you wake up, you get coffee, you try something, and you don't get results until the next day. So you're just kind of sitting around all day trying to do something else. We think the ideal life of a data scientist is get a cup of coffee, or launch a job, get a cup of coffee, come back, look at the results, analyze, do it again, go talk to a colleague, come back, look at the results, do it again, and have a productive day. So all of these things that we're talking about to accelerate what the data scientist does is really so that they can be productive in a positive way where they can get results faster. So that's why we're talking about speed. We're talking a little bit about large scale, especially if you end up building models that you can then take on to larger systems, like the research system at Oak Ridge National Lab is, in real life, your data sets will be a lot bigger than demo data sets, for example. And so that ties back to the fast, because if you have a lot of data, it does take a lot of time to process. And then why does it matter to be fast and savvy with your data? Is because resources are expensive, whether it's cloud resources or infrastructure that businesses or universities build up for you. So the more effective you are at using the resources, and the more efficient your jobs are, the more work gets done with those same resources. So going back to the SnapML library, this is a list of techniques that are supported already. You can see they were wisely picked relative to how popular they are and how useful they are. And as I mentioned, the neural network piece is managed by a different set of libraries that I'll talk about in a minute. And there's a lot of work going on Bayesian techniques and ensemble methods as well. So, and then when you get down here, CNNs and RNNs, you're back into the deep learning territory as well. So this is definitely something to consider to accelerate, is the SnapML libraries if you're doing these kinds of techniques in your models. And here's some examples of SnapML performance relative to scikit-learn. And again, you saw the Zurich Research Lab is heavily involved, and I put the website and their publication relative to that. Any questions on SnapML?
So it's basically about the training for random forest to GPU and
Right. It's anywhere you would have used the scikit-learn routine, you could replace it with the SnapML equivalent, and that speed up is built in. And you saw in the video, there's single server version, and then there's a distributed version in the Power AI toolkit.
And is this a software solution, or it has to go with your server?
This It's set up to run on Power systems. I believe it can run on other platforms as well. Any other questions? Okay. So this is another set of tools. This is in tech preview for the software stack that you have. This is kind of the model of this toolkit, because people always want to be on the latest TensorFlow, on the latest this and the latest that. So the development process is agile on Power AI, and so we'll introduce things as a tech preview, vet them out, and they'll show up in the next release as fully supported. So right now this is in tech preview. This is NVIDIA's a group of accelerated libraries for machine learning. And they have two different things that are in the Power AI distribution. One is, I call it CUDA-DF, but it's CUDF. And it's a data frame library. Who here uses pandas? Everybody who's a data scientist, yeah. This is a GPU accelerated version of some functions of pandas on the Power, on our Power platform with GPUs. It also works on their platforms as well. But you can go and see what functions are supported, and there's a lot of good information on the rapidai.com website, and they're also on GitHub. But you don't have to go to GitHub to use some of the functions, because everything in the 0.2 version is already installed and packaged for Power AI 1.6.0. If you want to go to a later version, you have to build it from scratch through GitHub. Any questions on what this does? Just think pandas with GPU acceleration on some functions. Here's a little example of how you would do this. And I'll just point out where the difference is. Instead of importing pandas, you import CUDF. And here, to create your data frame, you do CUDF.read_CSV, which would be the same as you would. And then what this actually does is it takes, and you actually can see it on Kaggle. It's a tip database. So restaurant tips. So it's how many people in the party, whether they ate in the afternoon or in the evening, and what amount of tip they left and what their bill was. So this basically takes the tip and calculates the percentage tip times to get a percentage, and then it groups by the party size. So how many diners were there. And so the output, and so this is just regular, it has nothing to do other than the fact that you use this to read in the data set. But the output is party of 1, I guess they feel guilty, so they tip nicely. And party of 3 and 4 are cheap. And then party of 6, they also feel guilty because they usually leave a huge mess. So they tip a little bit better than party 1. So that's just a fun example. But again, the idea is to use a pandas like APIs, and so it's a conversion is fairly straightforward if you want to use this function that are in that library. They did the same thing with some machine learning algorithms. So I apologize for the line is exactly across the, hard to get better halfway through. Basically, it's mathematical primitives like matrix, multiplies, and so on that are used in machine learning, and standard machine learning algorithms. So again, the 0.2 is there and ready to go, and it has a whatever was supported at that time. They have a few more that are supported. And it's basically k-means, principal component analysis, DB scan, which is, and noise, application noise. I forgot what it was, but it's basically k-means where you can have data points that don't belong to any cluster, and you don't specify the number of clusters a priori. So, huh? Density based, thank you. The DB was escaping me. All right, so here's a little example for this. So the library is called CUML. So same thing, you use the data frames. You don't have to, you could use pandas, but you use the Rapids data frames library, the machine learning, and you import this algorithm, which is the one we just talked about. And you define and populate the data frame, and you basically run the model with EPS is the error rate, the farthest from the cluster that you want to be in any given cluster. And this is the minimum number of samples that you want in your, that you have to have in your cluster. Did you find a problem on the code? Yeah? No?
No, I just know.
Oh, okay, because bring it. That's how we learn, right? So this basically gives you, remember, you don't specify how many clusters you want up front. So this gave you 3 clusters, since the minimum sample size was 1 per cluster. So that's a super simple example, and I think that's it for the presentation. We can go into the Power AI product itself on our systems, and I can show you kind of where to look for the READMEs, because they will be your friend as you try to implement any of these techniques. So to recap, the techniques I talked about were the obvious one of adding more resources, but how you use those additional resources is where you can start using some of the software techniques, which is consider large model support if your data set is indicative of being able to take advantage of that. Consider distributed deep learning. I tend to use DDL-TensorFlow. There's also a cafe version of distributed libraries. And you saw SnapML has a distributed version for machine learning algorithms. Consider using the SnapML set of libraries and the Rapids set of libraries to accelerate your current models. Any questions? Yeah.
Just to be clear, we are not required to use any of these resources?
No. No. The requirement is to show a benefit on power systems with GPUs at scale, which is scale defined as more than 1 GPU. And ideally more than 1 node, but that'll depend on whether your model benefits from that. Okay, so should we stop the recording? I think we should, because the rest of this will be kind of ad hoc. So, any questions from anyone on the phone? I always forget to ask. Yeah.
Can I ask a question?
Yeah.
So you, like in one of the earlier slides, you talked about the Power AI, like the 3 different families, kind of. So we have access to you said the community. I forget exactly.
Community, yeah. Watson Machine Learning Community Edition, also known as Power AI Base, which is what probably you guys call it still, because we have to. I don't even think it's official yet, so we'll get there. Okay. So that's the base. The next level is called Watson Machine Learning Accelerators without the Community Edition, and that's the one that has the resource scheduler, resource management, deep learning interface, and hyperparameter support, and going beyond, 4 or 16 nodes in
Okay.
scaling. And then the other two pieces are add-ons, if you will, for non-data scientists. Point and click vision models with AI vision and point and click structured data models through H2O driverless AI.